Imagine you're handed a scatter of dots on a flat plane. Some are painted blue, some orange, and they're tangled together in a shape no straight line could ever separate. Your job sounds simple. Draw a boundary that tells blue from orange, so that when a brand new dot appears, you can guess its color. This is the heart of classification, and today we'll solve it with something surprisingly humble and surprisingly powerful. Before we throw any math at this, let's just look. Notice how the blue and orange regions curve around each other. There's structure here, but it's not a clean line. A good method has to bend and wrap to follow that structure without inventing structure that isn't really there. Hold that tension in mind, because it's the whole story. Our first tool is called a decision tree. The idea is almost childishly simple. Instead of drawing one clever curve, we ask a sequence of yes or no questions, and each question is about a single coordinate. Is this point to the left or right of some vertical line? Is it above or below some horizontal line? That's all a tree is allowed to do. Let's watch it make its very first decision. The tree scans every possible vertical and horizontal cut, and it picks the one that best separates blue from orange. Here, it chooses a vertical line right about here. Everything to the left leans orange, everything to the right leans blue. It's crude, but it's a start. Now here's the key move. The tree doesn't stop. It takes each half and asks another question, splitting again. The left region gets its own horizontal cut. The right region gets a different one. Each split carves the plane into smaller and smaller rectangles, always with edges parallel to the axes. This is why we call them axis-aligned boxes. The boundary a decision tree draws is never a smooth diagonal or a graceful curve. It's a staircase of rectangles, each one a little territory that the tree has claimed for blue or for orange. Keep watching how these boxes will multiply. Let me show you the tree itself, the actual structure behind these cuts. At the top is the root, the very first question. Each answer branches down to another question, and another, until we reach a leaf at the bottom. A leaf is a final verdict. This little box is blue, or this little box is orange. To classify a new point, you drop it in at the root and let it fall through the questions. Left or right, up or down. It tumbles down the branches until it lands in a leaf, and that leaf's color is your prediction. Watch this test point travel down the tree and arrive at its answer. So far so good. But a tree that stops early is often too simple, leaving whole regions mixed. So the natural instinct is to let it keep growing, split more, ask more questions, carve smaller boxes, and if a little growth helps, surely more growth helps even more, right? Let's find out. Variance is about how spread out the darts are. If your throws scatter all over the board, sometimes near the center, sometimes way off, that's high variance. Each individual throw is unpredictable. Even if they average out to the center, any single one could be far off. Now put these together into 4 cases. Low bias and low variance is the dream. Tight cluster, right on the bullseye. High bias, low variance, tight but off-center. Low bias, high variance, centered on average but wildly scattered. And high bias, high variance, the worst of both. So where does our deep decision tree sit? It's flexible enough to fit almost any shape, so on average it isn't systematically wrong. That's low bias. But it's wildly sensitive to the exact data, scattering all over. That's high variance. Our tree is the low bias, high variance corner, centered on average, but any single tree is a wild throw. And here's the beautiful thing about high variance. If your throws scatter around the bullseye but average out to the center, then averaging many throws lands you near the center. The scatter cancels out. What if we could do that with trees? Grow many wild scattered trees and average them into one steady answer. This is the entire idea behind a random forest. One tree is a single wild dart. A forest is a whole crowd of them, and we let them vote. If the errors of individual trees are scattered in different directions, then averaging their votes should cancel the noise and leave the real signal. Let's build it carefully. But there's a catch. If we grow 100 trees on the exact same data, they'll all be identical. 100 copies of the same wild dart is still just one wild dart. To make averaging work, the trees must be different from each other. They need to disagree. So we deliberately introduce randomness in 2 clever ways. The first trick is called bootstrap sampling. Instead of giving each tree the full dataset, we hand it a random sample drawn with replacement. That means the same point can appear more than once, and some points don't appear at all. Each tree sees its own slightly distorted version of reality. Let me make that concrete. Picture the original points in a bag. To build one tree's dataset, we reach in, grab a point, note it, and toss it back. We repeat until we have a full-sized sample. Because we put each point back, popular grabs get counted twice, and unlucky points get skipped entirely. The second trick is even more surprising. At every single split, when a tree is deciding which cut to make, we don't let it consider all the features. In our two-dimensional world, that means at each split we might restrict it to only the horizontal axis, or only the vertical axis. We hide options on purpose. This feels counterproductive. Why handicap each tree by hiding good options? Because if every tree could always pick the single best split, they'd all latch onto the same dominant feature and grow nearly identical. By forcing variety at each split, we guarantee the trees explore different structures and make different mistakes. Diversity is the whole point. So let's grow our first forest tree properly. It gets a bootstrap sample of the data, and at each split it can only see a random subset of features. It grows deep, just like before, ending up jagged and overfit. On its own, it's still a wild dart. Here it is. Now the second tree. Different bootstrap sample, different random features at each split. Its jagged boundary looks related but clearly distinct. Where tree 1 drew a spike, tree 2 drew a notch. They agree in the obvious regions and disagree in the messy borderlands. That disagreement is exactly what we want. Let's keep going. Tree 3, tree 4, tree 5. Each one is grown on its own resampled data with its own restricted features. Watch the pile of jagged boundaries accumulate. Individually, they're all messy and unreliable, each confidently wrong in its own peculiar way. Now for the magic. To classify a point, we don't trust any one tree. We ask all of them and take a vote. This test point. Tree 1 says blue, tree 2 says blue, tree 3 says orange, tree 4 says blue, tree 5 says blue, 4-1 for blue, the forest says blue. Notice what just happened. Tree 3 was wrong, fooled by its own overfit spike, but it got outvoted. The one tree that memorized noise in that spot was overruled by the 4 that didn't share that particular mistake. The crowd corrected the individual. This is the ensemble absorbing one tree's error. Now let's do this vote not for one point, but for every point in the plane at once. For each location, we ask all the trees and color it by the majority. As we sweep across the whole plane, the forest's combined decision boundary emerges. Watch what it looks like compared to any single tree. There's a subtle trade-off hiding here too. Restricting features at each split makes individual trees a little weaker, a little worse on their own. But it makes them much more different from one another. And it turns out a crowd of diverse, mediocre trees beats a crowd of brilliant but identical ones. Diversity wins over individual strength. Let me also dispel a worry. With a single tree, growing deeper eventually hurt us through overfitting. But adding more trees to a forest does not overfit in that same runaway way. Each new tree is just another vote in the average. More trees make the estimate steadier, never wilder. You can't have too many. You only hit diminishing returns. Let's step back and see the full arc on one screen. On the left, a lone tree, sharp, jagged, memorizing noise, brilliant on training data and brittle on new data. On the right, the forest, smooth, confident, robust, built from hundreds of those same flawed trees voting together, same building block, transformed by the crowd. There's a piece of quiet elegance in the bootstrap trick worth savoring. Remember that each tree skips some points entirely, the ones never drawn into its sample. Those left-out points are, for that tree, unseen test data. So the forest can grade each tree on the points it never saw, estimating its true performance for free, without setting anything aside. So let's name the principle that ties it all together, because it reaches far beyond trees. When you have a method that's flexible enough to be right on average but too jittery to trust once, the cure is not to make it simpler. The cure is to make many diverse copies and average them. Wisdom of a well-designed crowd. This idea, averaging away variance from high-variance learners, is called bagging, short for bootstrap aggregating, And the random forest is its most beloved incarnation. The trees provide flexibility and low bias. The randomness and averaging provide stability and low variance. Together they hit a sweet spot that's remarkably hard to beat. And that's the whole journey. We started with one tree carving the plane into rigid boxes, watched it grow so eager that it memorized noise, and diagnosed that failure as high variance. Then we planted a forest of deliberately different trees and let them vote, watching their scattered errors cancel into a smooth, trustworthy boundary. The next time you face a hard, tangled problem and a single clever model keeps flip-flopping on you, remember the forest. Don't chase one perfect answer, gather many honest, imperfect, independent guesses, and let them average out. The bias stays low, the variance melts away, and out of the noise emerges something that actually works. Thanks for watching. If this made it click, subscribe for more visual math.